we're starting a new unit, which is stoichiometry. So this cartoon here I just put up because we're actually returning to the mole. So this is, I just thought was a funny little comic to illustrate that. So the mole is back.
Chocolate.
Okay, so when you're doing any kind of recipe, you are usually making some sort of adjustments. If you're cooking for a bake sale at school, you may decide you need to make more cookies than 3 dozen. If you discover that you do not have enough butter, for example, for this recipe, like you only have a half a cup of butter instead of 1 cup of butter, then you would likewise cut all the amounts in the recipe to half. So, looking at this recipe here, we know that for 3 dozen cookies, we need 2 eggs. And if we're using 2 cups of chocolate chips, we know that we likewise need 1 cup of butter. But if we want to make changes, like if we want to make 9 dozen cookies instead, we would have to triple everything in the recipe. And let's say we looked at our cupboard, we want to make more cookies, and we knew that we had 1.5 cups of white sugar instead of 1/2 cup. We would likewise try to make adjustments with all the other ingredients to be able to match that. So, this is a technique that we kind of do naturally when we're cooking, and chemists also do in the lab, except what they're working with instead of cups and such are grams or molecules or moles. Okay, and we're also working with chemical compounds as ingredients. So, usually when we're in the lab, we're not making something we can actually ingest. So, also keep that in mind. Okay, so when we're looking at a reaction, it tells us how much we need of everything in our reaction to get the product. And this is kind of like our cookie recipe. So our balanced equation is like a recipe. So for example, here we have a recipe for making sodium chloride. We do this by combining 2 moles of sodium. So each of these coefficients now symbolize moles with 1 mole of chlorine, and this will make 2 moles of sodium chloride. And just like with our cookie recipe, a lot of times we do not want to make exactly 2 moles of sodium chloride. We may have a larger amount that we want to make or a smaller amount we want to make. We then make adjustments to our recipe or our reaction. So if we want to make 4 moles of sodium chloride instead of 2, we would have to double everything in our recipe or in our reaction. If we wanted to make 10 moles of sodium chloride, we would have to multiply each of our starting materials by 5. So we would have to make adjustments. So this is the process that we're doing with stoichiometry. We're evaluating our reaction and doing calculations based on our balanced equation. So stoichiometry, it comes from a Greek word which means measuring elements. And what we're doing are we doing calculations of the quantities in chemical reactions, and we're doing this based on our balanced equation. So to help us to set up problems, we're going to be using a concept called the stoichiometry island. And this is really just a tool to help you to set up problems. And as in the mole unit, it's also very important that you're following the units. Some of you guys will be able to set up your problems pretty easily by just following the units. Some of you guys might find it more helpful to use the stoichiometry island as a device to help you to map out how you're going to solve the problem. So we're going to be using 1 mole is equal to 22.4 liters as a conversion factor sometimes. 1 mole is equal to molar mass to help us set up conversion factors. And also 1 mole is equal to 6.02 times 10 to the 23rd particles. So we're going to be revisiting all those concepts from the mole unit. So I want you to write down or copy the stoichiometry island diagram into your notes. So I would recommend you set aside either a half a page of a piece of paper or an entire page of a piece of paper. And I would also recommend that you use like different colored pencils or pens to help you to make it more clear on your piece of paper. So in the stoichiometry island, you have substance A, which is our starting material. This is going to be our known. And then substance B, which is our unknown, and that's what we're trying to find. A lot of this will be familiar from the mole unit. So we have mass to mole is going to be converted using molar mass. Volume to mole, those are going to be converted using molar volume. And then particle to mole is going to be converted using Avogadro's number. The thing that's new with our stoichiometry island diagram is we're going to be using coefficients from the balanced equation to go from moles of our known to moles of our unknown. So just copy this down, and then we're going to work through some problems so you can see the process of how we're going to use this. Okay, so hopefully you have that copied down. We're going to focus first on just going from mole to mole because that's going to be something new. What you're going to notice is that the rest of the stoichiometry island diagram is going to be very similar to the mole as the heart. So when we're going towards the mole, in each case, on the left-hand side, we're going to be dividing just like we did with the mole unit, going from mass to mole, volume to mole, or particle to mole. When we're going away from the mole, just like in the mole unit, we're going to be multiplying by either molar mass, molar volume, or Avogadro's number. Okay, so when you're doing a mole-to-mole problem, and that is in the middle here, going from mole to mole using our coefficients, what we're going to have is we're going to have to first write a balanced equation, just like we did with the chemical reactions unit. We're then going to write something called a mole ratio, and this will be more obvious exactly what this is as we work through some problems. So right now, I just want you to write down that a mole ratio has your moles of your required, this is your unknown, over the moles of your given substance, this is your known. And then we're going to set up the problem like a unit conversion, just like we did in the mole unit, and solve. So just write down those steps. Okay, so let's look at a problem, and I'm going to show you how to set up this mole ratio. So I'm actually going to go into the mode where I could write on this slide, and we're going to do this problem. So first thing you're going to have to do is you're going to have to write out your balanced equation. Now, this one's a little bit different from our typical decomposition reactions from the reactions unit. So what we're going to do here is we have KClO3, and when this decomposes to KCl plus O2. And just like in our reactions unit, the first thing we're going to do is we're going to just balance our equations. So to help us to balance the equation, I'm going to put lines in front of each of the reactants and products, and then we're going to add coefficients. So I'm going to start with oxygen since that's not balanced. So if you remember, 3 and 2 both go into 6. So I'm going to put a 3 here, a 2 here, and then a 2 here. So now it's balanced. And what I would recommend is when you're doing these is to write down the information you're given in the problem underneath your balanced equation just to help you to organize what you need to do. So we notice here we have 9 moles, and this is of oxygen gas. So the number you're going to be given is going to be given with a unit, And it's going to be one of these three things in your reaction. This would not refer to oxygen within this compound. If it were potassium chlorate, it would say 9 moles of potassium chlorate. So this is 9 moles of oxygen. So that's what we're starting with. It's asking us how many moles of potassium chlorate. So you want to look for where it says how many or how much of something. So this is actually what we're looking for. So this is going to be a question mark, and I would put down what unit you're looking for, just to help you to see what kind of problem you need to be doing. So we're always going to put what we're given in the problem, our known. So this is our known, and that's substance A, and this is our unknown, and this is B. So if you go back to our island, we're starting always with substance A. This is always going to be our known. So you might want to label this. This is your known, and this is your unknown. And you might also want to label that you're always dividing on this side, and you're always multiplying on this side. Okay, so right now we're just going to do our mole ratio. So you might also want to label this as your mole ratio. Okay, so let's go back to the problem. Okay, so in our problem, we're given 9 moles of oxygen. So in this unit, I want you to label what compound or what element is with each of your units as you set up your conversion factors. And if you don't do that, you will get points taken off. So now we're going to write our mole ratio. So I'm going to show you how to write that. So we're going to have, and this is our mole ratio. So you notice here we have moles of oxygen, and we're looking for moles of potassium chlorate. So we want to match up not only the unit now, but also the compound or element at the bottom of our conversion factors. So the bottom should have moles of oxygen, because now we're not only trying to get rid of the unit, but we're also trying to get rid of which compound or element that is. Now you notice here we're looking for potassium chlorate. That's what we're trying to find. So that should go on the top of our conversion factor because that's our unknown compound. That's our B. So we're going to put moles of KClO3 on the top. Now, when we look at our equation now, we're going to use our coefficients in our balanced equation to use as numbers in our mole ratio. So let's look at our balanced equation. If we go up to the equation, we see that we have, and I'm going to use blue here, we want to look for moles of O2. So our number with O2 in our balanced equation is 3. So that is what I'm going to put into next to moles of O2. Likewise, if we go up to the top, we're going to look for moles of KClO3. So we look for KCl3. The coefficient there is 2. So let's put a 2 here. Okay, so in your calculator, you're going to be multiplying what's on the top divided by what's on the bottom. So we're going to multiply 9 times 2, which gives us 18. Divide that by 3, and that should give us 6. That is our answer. For sig figs, we only consider what the problem gave us. So it gave us 9 moles. That's one significant figure. So our answer is likewise going to have one significant figure, or 6 moles. Okay, so what I want to do now is I'm going to actually pull up your worksheet that you have for homework, and we're going to do one of the problems from that sheet. Okay, so this is your stoichiometry problems, mole to mole. And let's look at one of the problems. So let's go down and do number 2. Okay, so we're going to first write our balanced equation. So we have hydrochloric acid reacting with zinc, producing hydrogen gas. So HCl plus zinc, and one of our products is hydrogen gas. Now, if we look at this, we can see right away there's no way to balance that. And that is because we do not have all the products. So remember, when you see an element in a compound, this is a single replacement reaction. So remember, with zinc was kicking out hydrogen. They're both on the left-hand side of our activity series. So hydrogen ends up by itself, and then zinc combines with chlorine to form a compound. We have to use the charges when zinc is in a compound, which is 2 plus. So remember, zinc 2 plus, chlorine minus, that gives ZnCl2. The next thing we want to do is we want to balance our equation. So here I'm going to add lines, and we notice right away hydrogen and chlorine are not balanced. So we're going to have to add a 2 on the reactant side to balance those out. And now we see it's balanced. The next thing you want to do is you want to look for the number in your equation. So we have 0.4 moles of hydrogen gas. I'm going to write that right underneath the hydrogen. So 0.40 moles. Now, what we're given, this is our A, this is our known, can be either a reactant or a product, and our unknown likewise can either be a reactant or a product. So don't assume it's going to be on a certain side of the equation. So you notice here, it's asking us how many moles of hydrochloric acid. So that is going to be what we're looking for. This is our B, this is our unknown. Okay, so we're going to write what we know are known over here. This always goes over 1. And then we're looking for moles of HCl. This is our B. This is our A. Okay, so now remember we have moles of H2 at the top here. To cancel that out, we have to have moles of H2 on the bottom. We have moles of HCl, which we're looking for, so that's what's going to go on the top. So remember, your mole ratio should always be your B over your A. So this is our B over our A. Okay, now we're going to go up to our balanced equation to look for the numbers that go with H2 and that go with HCl. So we have moles of HCl in the denominator here. So we're going to look at, H2 in the denominator. We're going to look up here. We see there's a 1. So I'm going to put that in blue so it stands out. So that's a 1. Now, if we go up to our balanced equation again, we're going to look for, and I'll do this in orange, HCl. We look for HCl. We see that's a 2 there. So let's go back up, and we're going to put 2 here. So that's where these numbers are coming from. They're coming from a balanced equation. So now we're going to multiply what's on the top in the numerator, divide by what's in the denominator. So we do 0.4 times 2 divided by 1. That's going to give us 0.8 is our answer. And we know as moles cancel out, H2 cancels out, we're left with moles of HCl. Okay guys, so that's a process. So I want you guys to try some of these on this sheet and see if you have any questions.